Alright, so here finally is one of the two versions of the fundamental theorem of calculus, namely the theoretical version. Probably this is the version that you're less familiar with, but it's one that is really key. It's the one that allows you to get the familiar practical version, but also it's something that we need to use because it will be of interest later on. Alright, so what does it talk about? So let's say now I need a continuous functions to make things work. So let's say we have a continuous function f of x and the value a in its domain. Now, what the FTC says is that the derivative of the area function of this function f of x is actually the original function. So what this statement actually says is that in this situation, the derivative with respect to x, again, notice now the variable is the upper limit of our integral. So the derivative with respect to x of my area function is nothing but, right, so that's just a reminder, is the derivative of that definite integral. It's simply the function inside. So now you may say, oh duh, I'm taking the derivative of an integral, of course I'm going to end up with the original function. But remember, we're talking here not about indefinite integrals. We're not saying we're taking the derivative of an antiderivative. We're taking the derivative of the limit of a sum as n goes to infinity, blah blah blah, right? So it's the derivative of an area. So why should it be that in fact we are going to end up with the thing inside? Okay. Now, before I'll show you a little bit of a proof, let me point out that this statement also implies that the area function is one of the antiderivatives of the original function. We're going to figure out later which one. But this is what it says. The derivative of the area function is the function itself. This is the integrand. And therefore, the area function is one of the antiderivatives. Remember, it's not the general antiderivative because it's a single function. Eh? All right, so let's see. Can we prove this? Well, I'm not going to give you a full proof, but a little bit of a sketch of a proof. So here is a sketch of a proof, and I'm saying the sketch of a proof because I'm skipping some important technical details to make it a little bit more easy to understand, so you understand the real substance of it and why it's true, and it just convince you, yeah, this is not just something very complicated, it's something quite simple. There's just one or two little technical steps that need to be checked to make it into a formal proof. Okay, so the idea is the following. We have this area function, so the integral from a to x, definite integral of f of t dt. Let's compute the derivative of this function. Remember, we're computing derivatives with respect to x. Okay, so that's the upper limit of the integral. So the derivative is going to be, as with the usual definition of derivative, the limit as h approaches 0 of a of x plus h minus a of x all over h. But what do a of x plus h and a of x mean in this particular situation? Remember, both of them represent integrals. One of them is the integral all the way to x, that's a of x, and the other one is the integral all the way to x plus h. So that means the area shaded in green plus the area shaded in blue, right? So that's what it means. So what we're looking at is the limit as h approaches 0 of the difference between those two integrals. Remember, each one of those represents an area, and so the difference between them is just the same thing as 1 over h, well that's just doesn't depend on the integration, times the area of that little strip. Let me rewind and show you again. Okay, so I'm looking at the difference between those two areas. The one area is the area that is between the a and x plus h, so is the green plus the blue. The second one is just the green, so when we subtract them we end up with this one, which is just the blue area. Okay. Now, if you notice, this area is roughly the same as the area of this rectangle. Not quite the same, right? But the only difference is that little section on top, and in fact, that difference between the area under the curve and the rectangle for this tiny strip is going to get smaller and smaller as h goes to 0, which is exactly where we're going. You can tell this is the one point where you need to check the details. Okay, so here I'm waving my hands a little bit, but I hope you believe me when I'm saying that that integral from x to x plus h is in the limit the same thing as the area of the rectangle, which is of course f of x times h. Again, technicalities to check, but they work out. So now at this point, the h's of course cancel, in which case the limit really doesn't play any role anymore, and so what I'm left with is my f of x. And notice where we've gone. We've started from the derivative of the area function, and we've concluded that it's equal to the integrand, which is exactly what the fundamental theorem says. Okay? So this, again, not a full proof, but a sketch of the important ideas of the proof.